Strength of acids and bases deals with when you have a strong acid and its conjugate base, or you have a base and its conjugate acid. How do you know in terms of which one is stronger and which one is weaker? Okay, and the general rule is the stronger the acid, the weaker its conjugate base. And also, vice versa, the stronger the base, the weaker its conjugate acid. Well, how does that, where does that come into play? Let's look at for an example down here a little bit further on. Here we have an example. This is a Bronsted-Lowry acid-base reaction. And here we can see the acid is donating the hydrogen. So here we see the acid and therefore the conjugate base. And therefore water in this case is acting as the base, and this is the conjugate acid. So you can see that there's two acids in both cases and there's two bases. And the question many times will come up, which acid is stronger, the acetic acid, the HC2H3O2, or the H3O plus, the conjugate acid on the opposite side? It comes back to the equilibrium constant, okay? If the equilibrium constant is less than 1, which we can see here that it is, that means we have mostly reactants. And if we have mostly reactants, that tells you that this reaction, that this acid dissociates easier than the other acid does, and therefore that makes it a stronger acid. So when the equilibrium constant, when K is less than 1, the strong acid is on the product side. Okay? Now, remember, the stronger the acid, the weaker its conjugate base. So therefore, because the equilibrium constant is less than 1, the conjugate acid is the strong acid, and therefore its base, which is over here, is therefore weak. So that is a weak base. And because this is the weaker of the two acids, that makes its conjugate base stronger. And this will always be the case. Whichever side the strong acid is on, the strong base will also be on the same side, as you can just see. Okay, so when K is less than 1, the strong acid is on the product side, so is the strong base. Okay? If K is greater than 1, again, let's think about that. Let's say it's 10 to the second or something like that. Positive 2. So when K is greater than 1, the strong acid and the strong base will be on the reactant side. Okay, and again, let's think about Y here. Let's get rid of the strongs here. If it is times 10 to the second, that means you have an equilibrium constant that's greater than 1. So that means you have mostly product. If you have mostly product, it means that this acid dissociates easier than the conjugate acid does. Therefore, that would make that the strong acid, and therefore its conjugate base weak. And therefore, if that acid is strong, this acid is the weak acid, or the weak base. The weak acid. And therefore, its base on the other side is strong. See how the strong ones are always on the same side? Okay, same case here. NH3 becomes NH4 plus, so it's a base, and this becomes the conjugate acid. And then if that's the base, then water is acting as the acid. In this case, it donates the hydrogen. It becomes the conjugate base. Because the equilibrium constant is less than 1, therefore that makes the strong acid on this side of the equation, which means this acid is weak. And therefore, if the conjugate acid is strong, that means the base on the other side is weak. And this acid here is weak. That means its base is strong. And see how the strong acid and the strong base, again, are on the same side. The weak acid and the weak base are on the left-hand side in this case. Okay, so that's really what you need to know about using equilibrium constants to determine which acid is the stronger acid or which base is the stronger base. You use the equilibrium constant to figure out which acid is stronger, and then use that to figure out which base is therefore stronger. Okay, and again, this really only applies to weak acid situations. Okay, remember that that when you're dealing with the solubility rules, if you have one of your 7 strong acids, which again, you really have to have those memorized, okay, that they don't form equilibrium systems at all. Notice that arrow there is just an arrow completely to the right, which means they completely ionize when you put them in water, which means that if you have a 0.5 molar solution of HCl, and you need to know the hydrogen ion concentration, the hydrogen ion concentration is also going to equal 0.5 molar, because for every 1 HCl particle, you're going to get 1 H3O plus particle. Okay, or you just write it without the water in there, and again, 0.5 molar HCl is going to have a hydrogen ion concentration of also 0.5 molar. Okay, and then same with the base here. We know that the strong bases, again, are the alkali metals, calcium, strontium, and barium, and then also ammonium. So anything that has a hydroxide with an and it's usually an alkali metal, will completely dissociate. Again, whatever, if this is 0.25 molar NaOH, then the hydroxide ion concentration is 0.25 molar. Again, there's no equilibrium signs because it does go completely to the product side. And HCl is a much, much, much stronger acid than H3O plus, and Cl minus, the conjugate base of the strong acid, is a very weak base. Okay, and this is true of all conjugate acid-base pairs. A very strong component, if it's a strong acid, just like we just talked about, it always results in a weak partner, the base. If it's a strong base, then it has a weak conjugate acid. Okay, now in the cases of weak bases, or acids, and all of the other acids or bases that they mention will be weak. If it's not one of the strong acids or strong bases that we've learned, then they typically have very little ionization. There is an equilibrium system set up, and typically that lies heavily on the left-hand side, the unionized form. So in most weak acid, weak base situations, and both of these fall into that category, because that equilibrium is so small, it means that you have mostly reactants. Okay, you have very, very little of this, very, very little of this. You have mostly the molecular form. This is the molecular form, the unionized form of that acid in that equilibrium system. Okay, and again, those equilibrium constants tend to be very, very small very small numbers, which means you have a very small amount of product in your equilibrium mixture. So our examples of acids and bases, again, here are the 7 strong acids. The strong bases, again, we could throw ammonium hydroxide in there as well. That certainly is a strong base. And again, don't even think about memorizing weak acids and weak bases. It's anything that's not one of these in terms of acids or one of these in terms of bases. And they, again, will always tell you, trimethylamine, a weak base, blah, blah, blah. Okay? So down here we can see just a couple of examples here. Consider the 4 diagrams below, where in each case HA is an acid represented by the green and the pink circles together. H plus is a hydrogen ion, is represented by the green circle. A minus is the pink circle. Okay, which of the diagram represents a relatively concentrated weak acid? So again, a strong acid is going to be completely dissociated, whereas a weak acid is not going to be completely dissociated. So we can see in A and B that a lot of those molecules, a lot of those acid particles are still together. So in both of these, we would say that is weak. And which one has a greater amount of particles per the number of water molecules? Notice that these are all the same. It's the number of water molecules that are present that change. Notice in B you have a lot less water, and so B represents a concentrated weak acid. Okay, because most of the molecules are undissociated and you have more particles of the acid per the volume of the solution. You have a lot less water in there. Okay, and then which diagram represents a relatively concentrated strong acid? So in C and D, we can see that they're completely dissociated. And again, in C, you have less water than you do in D. So C is a strong acid that is, again, more concentrated than D would be. Okay, and for the other two, so answer D would again be strong, but then it would be less concentrated. And then A would be a weak acid that also is less concentrated. Okay, so as seen from the example above and the chemical equations before them, the concentration of the hydrogen ions, and notice I say hydrogen ions when it's saying H3O+, that the concentration of the hydrogen ions and the hydroxide ions are dependent upon two completely separate factors. First of all, how strong the acid is. Okay, if the acid is a strong acid, of course you're going to get way more hydrogen ions than if it's a weak acid. Okay, and secondly, it's the amount of water present. So imagine you have a 0.5 molar solution of HCl and you have a 0.5 molar solution of HNO2, which is, again, this is strong and this is weak. Okay, which one has a greater number of hydrogen ions? Which one, certainly HCl is a stronger acid. Which one has a greater number of hydrogen ions in it? Absolutely is this one. All of those H's that are here will convert to H pluses. So you have 0.5 molar HCl. Because this is a weak acid, we don't know right now what's the concentration of hydrogen ions in that solution. We don't know. Okay, and we don't know because we don't know the equilibrium constant. We don't know how much of that HNO2 is going to break apart into ions. Okay, and we're going to get to that in just in a future video. Don't worry about that. Okay, but we can't predict just based on this how how many hydrogen ions there are. Okay, and if you think about it, let's say we had 0.75 molar HNO2. Now do they have the same number of hydrogen ions? I doubt it, because again, without knowing the equilibrium constant for HNO2, I don't know. But all I know is you would have to have a way, way, way bigger concentration of HNO2 in order to get the same number of hydrogen ions. Because again, every single one of these hydrogens are going to become H+. But with HNO2, very, very few of these are actually going to form and stay as H+, because again, you have that equilibrium system. So let's say we have 2.5 molar HNO2. Still, most of that HNO2 is going to remain as HNO2. Very, very little of it is going to break into H+. So you have to have a much, much higher concentration of a weak acid to get the same amount of hydrogen ions or the same concentration of hydrogen ions in that weak acid solution as you do in the strong acid solution.